we will there we go. All right. Good afternoon. Welcome to the Northwest Institute for Cybersecurity Education and Research, or CySER, virtual seminar. And today we're fortunate to have Jim Alves Foss from University of Idaho. And Jim joined University of Idaho 30 years ago after receiving his PhD in computer science from University of California, Davis. He taught U of I's first cybersecurity class in the spring of 1992 and is director of University of Idaho's Center for Secure and Dependable Systems. He has over 125 peer-reviewed conference and journal papers in the cybersecurity area and has mentored 22 PhD students, over 40 master's students, and numerous undergraduates. His research has been sponsored by federal agencies, including NSF, Department of Defense, and industry. And for his efforts and activities at University of Idaho, he's been recognized as a distinguished professor, which is the university's highest honor, highest faculty rank. And today he's going to talk about probabilities, percentages, and professions of performance. So, Jim.
All right, thank you. So so my name is Jim Alves Foss, and as was mentioned, I'm director of the Cybersecurity Research Center for Secure and Dependable Systems at the University of Idaho. Wanted to tell you just a little about our center first. We do offer undergraduate and graduate certificates in cybersecurity. We offer a bachelor's and master's in cybersecurity. The BS consists of several computer science courses and 12 cybersecurity specific courses, starting from a freshman intro to cyber all the way up through advanced vulnerability analysis and forensics. The MS requires 4 cybersecurity specific courses and then several electives with thesis or project. The university has hands-on air-gapped lab for cybersecurity experiments that protects the university network, and a power systems lab we do a lot of cyber experimentation in. For research, we do research in a wide variety of areas for cyber, binary analysis, design and analysis of secure systems, industrial control system security, specifically with respect to the power grid, forensics, side channel analysis, secure software engineering, etc. Now I noticed a typo here. We have 12 plus, that's just a 12 plus faculty who are specifically doing cybersecurity research, 6 in computer science, 5 in EE, or ECE, electrical and computer engineering, 1 sociology faculty member, 1 business faculty member. We have several others who work with us occasionally on different projects. The history, was mentioned, I taught our first cybersecurity course in 1992. We've been a National Center of Academic Excellence since 1999 in cybersecurity, and an NSF Cyber Corps Scholarship for Service School since 2001. And I realized I mentioned the number of faculty there again. So today, though, what I wanted to really talk about and spend some time talking about was what I'm calling percentages, probabilities, and perceptions of performance. The idea that basically, as a cybersecurity researcher, researcher in general, but I'm going to talk cyber, we read a lot of papers, and those papers are not necessarily forthcoming on all the information. And I want to talk about that some so that people understand when they're becoming a cybersecurity researcher or when they're out publishing their own papers, they're doing it in a way that's more beneficial to the community. So if we talk about it in general, when we have experimental computer science or cyber results, several of these papers compare the results of some tool or some algorithm to some other tool, some other algorithm, or maybe they compare it across different data sets that they have. Now, we have to understand these papers are written to show successful results, but often with limited information and poor statistics. They're telling everybody, hey, well, let me go on the next slide. Never mind, it's later. We tell everybody basically my tool is better than their tool, therefore I can publish the paper. If I have if I write an algorithm and said, hey, this algorithm is worse than the other published algorithms, they don't accept it. So I will.
Jim, did we lose you? Can you guys hear me?
I think he's frozen.
Yeah, I think he's frozen.
So we could, how can we do it? We could do it.
He said he had an issue. So there's a phone number he could call in on and we can change the slides.
Sure.
Well, I guess we can't change the slides unless he
We'd have
sends
to-
us.
Yeah, let's email him and see if I'll do that.
Next door and knock on his door.
Oh, he's going to knock on his door. Okay.
Odd, because I'm right next door and clearly am not having a problem.
Yeah. He might be able to come to your office, Terrence. Maybe that's the easiest.
Well,
Okay,
he
so
said his computer.
how far back did I go? When did you lose me?
You were on slide 4.
Okay, so it didn't lose me much. Sorry about that. I don't know what happened.
Oh, you're back. Good.
You said
am
your
back.
your computer was having issues. So
This, I wasn't seeing any issues here. Just suddenly it said you're out of the meeting. All right, so I apologize for that. We'll try some more. So I see what happened. The icon for this meeting was on the wrong window, so when I hit return for the next slide, it hung me up. Okay, so let's talk about an example. This set for the context of what I'm going to talk about the rest of this. Compilers, it's a tool that translates source code, executable programs into a binary image, the actual executable image. So it takes our C source code, takes our a Fortran code, whatever, and turns it into an executable program. Inside that executable program, we often can have information about the source code. What we call a strict binary strips out all that information, all the symbol tables. So we don't know where functions are. We don't know a lot of information, debug information about the program. What's most important here, inside the piece of code, we have executable functions. We don't know where they start and where they end in that executable binary when it's fully stripped. The problem is exacerbated when we use different compilers, when we have different compiler options, different optimization options, or different programming languages we've chosen. The reason I talk about this is if I want to reverse engineer or decompile a program so I can do analysis on it, especially automated analysis, say unit level testing of the binaries, or I want to actually go and correct security flaws, go in and patch the binaries, I need to know where these functions exist because I need to know where the control flow goes as it calls and executes one function after another. And maybe I can even insert security protections. So the Darpa Cyber Grand Challenge was one example of something that actually did this. And several other Darpa programs. Okay, so this is the problem space we want to deal with. There's been some attempts at doing this. Bayo et al. Developed a machine learning based approach, and she tested it on Unix utilities for GCC and ICC. And the peers results incorporated into a tool that published. Shin et al. Did a neural network approach, tested on some other tools. GCC and ICC were two of the compilers they both used. Andresi et al. Developed a graph theoretic approach, used it for GCC and client compilers. So we see that there's different research out there. We can look at it. We want to now compare, say, a new result with this old result. How do we do that? Oh, I forgot to mention there's some commercial attempts to do this as well. IDA Pro, NSA's Ghidra. So how good are these prior approaches? When we're looking at this research papers, we want to figure it out. Now, they did several things I like. They used several different data sets, the bin utils, core utils, fine utils data set. There's 129 unique programs. They use the spec CPU benchmarks, which include some Fortran, C and C++ code. They compile them with the GCC compiler and or the Clang compiler and or the ICC compiler and the G-Fortran or iFortran for the Fortran versions. And they used 00, 01, 02, 03 optimization flags. Or even compiled the Chrome browser and compared it with things. So these are all the different data sets, and that's good. People have a lot of different data sets to look at. Now, they want to know, how do we measure success if we're doing something like that? We need to figure out what the ground truth is, what reality is. So we can use a simple table from the unstripped versions of the test suites. We can measure true positives. So we say this is the start of a function. That address is the start of a function. If we're correct, that's a true positive. If we're wrong, it's a false positive. If we didn't say anything about an address, didn't talk about it, it's a false negative. So when we're reporting the results, we say, hey, did we get the right location? That's our function start. Well, what if the symbol table has aliases? What if it gives multiple names to the same address? How do we count that? Some of the papers I looked at counted them twice. They didn't strip it out and their ground truth was wrong. Or function boundaries. Did I get the right length of the function? What if I'm too short? Is that okay? One of the papers I read actually said, if you're short, that counts. Other papers said you had to be precise. Knowing this when you read the papers is important. What if the symbol table showed a 0 length? Most symbol tables do for default functions. How does that count? Does the symbol table include padding bytes? One of the compilers does, the others don't. So these are all things, and I'm just throwing these out here to think, there's all these things we have to think about that a lot of the papers don't. So how's this get into now actually dealing with the results? This is what I really want to focus on. Prior work that we talked about in this research area used the concept of precision. Basically, how correct are our answers? Every time I said, this is correct, this is a function boundary. That's, if I was right, it's a true positive. If I was wrong, it's a false positive. So true positive divided by the number of times I said it was true. So the less false positives, the closer this goes to 1. Recall, how many functions did we find? So basically all the ones I found that were correct and all the ones I never said anything about, all the ones I was wrong, divided, number of reports I did divided by that gives us recall. And F1 is the weighted average of these two. I'll come back to that in a minute. What's important here is the results are based on the means of the results from our data sets. So what does mean mean? When I'm looking at this, I want to say I used the same data set for all the tools everybody else did. My numbers, my average over everything I did on that same data set is bigger or better than their numbers. I win, right? I get to publish my paper. My numbers are bigger. My numbers are better. But what we're not asking, what we're not looking at, what we're not seeing in these papers is, am I always better? If not, where am I better and why? If I'm not always better, if I'm worse, where and why? Maybe there's a few instances where I'm a lot better and these skews the means. Because I have if I took average salary of everybody at this meeting, I could get a reasonable number. If I throw in Jeff Bezos in this meeting and have an average salary, that average means nothing for everybody else in this meeting. Because that average is just so much higher. So we need to look at that when we're doing the data. And so many times I see published papers, published results that don't accurately look at this. I'm going to give you some examples. One, some people will say not only am I looking at the means, I'm looking at percentages. But again, what does it mean to have higher percentages? I'm better for all test cases or just some test cases? So Bayo et al., I mentioned their paper. This is the results of how they detected function starts. Using the GCC compiler or the ICC compiler, here was the precision. They compared to Rosenblum, who was one of the earlier works, and 3 variants of their own tool they call byte weight. Precision was 0.49, recall 0.43, and Bayo had 0.91 or 0.87, 0.98, 0.93, so much better percentages. 98% of the time when they said it was a function start, they were right. They got 93% of the function starts right using this technique. And their numbers were a little lower with ICC. Andretti et al. Used Clang and GCC and Visual Studio, and they looked at 32-bit and 64-bit code, and they compared IdaPro, the byte weight, Dynenst, another approach, and their approach, and they talked about how they win. The pluses are where they win, the minuses are where they fail. So here they're a little less, but here they're better. This is the typical type of thing we see in these publications. This is over all test cases in their data set that are 32-bit using this compiler. But did they really win? An average is just a single value. A mean is just a single value. That's all they're showing in this table. We can do better than that. I ask my students, I'm asking you, visualize the data, look at it, think about it. I could take, so as I mentioned before here, these are precision and recall. I could take the weighted average of these, calculate the F1 value. That's what I'm going to do. And I could graph it with a histogram for the combined data sets. And with a histogram, oh, here, I've got 98.2% bucket, the 97.28% bucket. I see a lot up here high, but it does trail down. And I see some things down here, some test cases were in the 65% or even 53%. There's something going on. The average is way up here, but this is interesting to me. So what I did is I took this work that I saw other people published. I reran the experiments, I took the data, I did a scatter plot. So they had two major data sets we used, the Unix utilities and the spec CPU benchmarks. And this is the F1 values for combined data sets. And the orange here, the spec, notice it's all over the place. That's interesting. Bayo et al. Did not even use that data set. They only used the blue one, and that looks better for their results. So maybe something's interesting. But what I find really interesting, besides this one data set being off, is these chunks. The average brings it all up, but if we look at these are interesting. This is where it matters. And so what I did, and I appreciate the work that Bayo et al. Did, when they ran their data set, they had their 129 programs, compiled with 2 different compilers, compiled with 4 different optimization options, compiled for both 32 and 64-bit. So as you can see, there's 16 variants of each of these 129 programs, and they named them based on those variants. So if the program was archive, it would be GCC _ binutils for the data set _ 01 for the optimization option _ 64 for 64-bit _ now the final executable name archive. And so you can sort based on different parts of the name and organize things. So here I broke things out by the optimization level and sorted them by their name. So it grouped them by data set. Again, interesting. So then we sat back and thought, how interesting is this? What's going on? Now notice, I got to be careful there. This stops at 80% at the bottom, 80 to 100, it's not 0 to 100. We got to look at this and we said, why might this be happening? We actually, because this was plotted in Excel, in Excel, I could hover over one of these dots and it tells me which row it was. So I can get which file name was actually had that value. I could look at that and I started noticing a pattern. Most of these were very small functions, very small programs. So we sorted them by size as well now. And notice the slopes here, especially this slope. What we found is some of these were using, again, interesting, they were using the same library that the compiler created that their tool could not detect. as a function start. Down here, these are the smaller file sizes. They had a higher percentage of undetectable functions than this did, even though it was the same group of 20 functions they couldn't detect. Here, there's a bunch of other functions that affected the percentages. So looking at the data and the way the data presents itself and the way this worked, we could start figuring out what was really happening. Much better than saying my answer is 97%. We can discuss about it, and we can discuss about why it struggled and where it succeeded. So now let's look at some different visualizations when comparing different tools for the results. Remember these tables. This is what we were seeing in the published literature. Tables like this. Can we do better? Let me look at one of the tools. This is a graph, a scatter plot of every test case, compiled with Clang, compiled with GCC, compiled with ICC. In the parentheses are the numbers we see in these previous tables. But this is the actual data. And you can see clustering and you can see groups. Now, all these charts, I'm going from 0 to 100. So you can see there's really struggles in some of these parts. With this Clang compiler, this tool struggled. This was the tool that the Bayo et al. Publication did. They didn't publish based on this tool. They published based on the other two tools. This was Nucleus. Again, from 0 to 100, clustering. They had problems with the ICC compiler. That's the one they didn't publish about. They only published with Clang and GCC, which are way much higher except for a few places. Ghidra didn't publish any of this, but we used it anyway to see where they do. Ghidra's optimized for GCC. They did excellent work with GCC, way up here in the purple. They struggled with ICC and with Clang, and you can see it and see where. So you can look at these different tools and see they behave differently with different data sets. And each one could claim they win if they reported just certain amounts of data or certain single numbers. IDA Pro struggled with even GCC, which everybody else did well on, and we stopped running the tests on it because it was too hard to run the tests, but I just wanted to show that. And here's our tool. We win. Not only are our numbers much better down here at the bottom in these single percentages, you can look at it. There were very few places we struggled. This is, going from 0 to 8 to 100%, just like the other tables showing it the same. And this as of October 2019, our numbers are even better now. If I blow it up to go from 85% up, we can still see there were a couple places we struggled in the Intel compiler and a few places with the Clang compiler. Some of those we've cleaned up now. But this is a way to show the data, to really examine the data. And why we were able to get to this is because we looked at charts like this. We said, why did this section fail? What is going on with our tool that causes this to fail? Is it something we can fix? And we did much better. But if I was just looking at these raw numbers, hey, my numbers are good, I'm done. That's not sufficient. All right. So that's just talking about the means and percentages. I want people to do more than just these tables, like this. I want them to give me information about the data. And even if I put in error bars or confidence intervals, that's better. It's still not enough. Yes, this takes up more real estate, but everything's electronic these days, so not too much. The other thing I want to, and I'm complaining here a little, I see people talking about, my tool is this accurate. Are they actually even using the right term for accuracy? In some of the papers I've read, the answer is no. So how accurate is accuracy? If we look at this, what we call a confusion matrix, my tool is predicting something positive. That's a function start. Or I found a virus on a virus scanner. I found an attack. Predicted negative. That network packet, that email does not contain a virus. That email is not spam. Would be a predicted negative, predicted positive, it is spam. Versus reality. condition positive. It's really spam or not really spam or not really spam, etc. So true positive, we say it's spam, it is spam. True negative, we say it's not spam, it's not spam. Well, we got some formulas here to tell us what these things are: prevalence, accuracy, precision, recall, and F1. I talked about these bottom three. Accuracy is, let's look at everything I said that was in the true positive and in the true negative divided by total. How many times did I get these two right? Prevalence is how many, we're looking at the percentage of times we're actually looking for the true positive out of the total situation. So let's look at this case. Ground truth, reality. Say I get 1,000 emails and 10 of them are spam, and I'm trying to detect spam. So 10 truly spam, 990 good. If I have a tool that is useless, that says nothing is spam, that tool is still 99% accurate because it got 990 out of 1,000 correct by saying they weren't spam. And I have seen people talk about this because they're not paying attention to what they're doing. This is 99% accurate and 0% useful. But it's still 99% accurate. So if we look at precision and recall, given the formulas, precision talks about how many of the predicted positives were correct, 0. Recall, how many of the true positives we actually said were correct, 0. The weighted average of that is 0. So 99% accurate, but precision, recall, and F1 are 0. And I talk about F1 a lot. It's an easy to use weighted average. There are others out there. Here, look at another example. Maybe there's 985, same example, but I reported it differently. I reported 985 negative, 5 positive. I reported 5 others positive I was wrong in, and I missed some. Well, this is now 50% precision, because I reported 10 positive, only half of those are right. 50% recall, because there were 10 actually positive, I only got half of them. Weighted average 50%, but I'm still 99% accurate because I got 990 out of 1,000 correct. So I hate accuracy, and people misuse the word all the time. In a case where we have low prevalence, a low percentage of the conditions you're examining are actually what you want, never use accuracy. Use something else. These are the areas that are relevant. The fact that there's a whole bunch of things that don't matter because they're negative shouldn't be looked at, shouldn't be counted. Precision counts the row, recall counts this column, and we never pay attention to this condition negative, predicted negative. For cybersecurity, a lot, when we're trying to find attacks, trying to find vulnerabilities, trying to find spam, trying to find viruses, other things, there's a lot. Where's my mouse? There it is. Next, know what's being measured. Understand what you're measuring. Understand your statistics. Present it reliably. Here's an example. Fuzzing is a tool that just throws a bunch of random data at your program to see if it crashes. Better fuzzers optimize the input to your tool to get more likely to find crashes. This is from a report that I found showing how well a whole bunch of different fuzzers, these are down here, did against a library. And so you can see this is reached region coverage and the different fuzzers, and they're charted, and here's their error bars, the distribution, and here's a chart of over time how well they did. And you look at this and you say, wow, they're doing really well. LibFuzzer wins, it's way up here. And then I look at the details. And I find that on average, so this is for LibFuzzer, the winning one, they only tested 38% of the functions. They missed a lot. And we noticed this piece of code, crc32.c, they tested 0% of it. 333 lines of code, they never executed. They never tested. zutil.c, they missed some. Here, they got 60% of 1,000 lines of code. So line coverage, totally 57%. Here, it looks like they're at 100%, almost 100%. They're doing so well. What they did is they graphed this based on how well the best tool does, and they round up and set that at the top line on the graph. So, hey, nobody did more than 1,000 lines of code or 1,000 regions, so we're going to set 1,000 as the maximum. But there's 1,664 regions. But all the reports and all the publications I'm seeing, or many of the publications I'm seeing out there, I'm seeing these graphs, these charts, because that's the available tool. That's what the grad students, I'm going to blame grad students run the tool, they see this, they don't think about it, their major professors then ignore it, and ignore this fact, publish this stuff, it looks good, we win, our graphs look chart, but in reality, we're missing half the code. So I want people to be clear on that. There's some other things I want to talk about briefly. When you're using statistical tests, make sure you're using the right tests. A lot of statistical tests, is tool A better than tool B? Assume your data is distributed randomly on a normal distribution. Well, you saw my histogram earlier, that's not a normal distribution. It had a long tail on one end. Using a student t-test or anything else won't work with that to say whether one tool is statistically better than another. And I've seen so many people just pick a tool, a statistics tool, because that's what they learned in their undergraduate statistics class. Instead of talking to a statistician. There's several different sign rank tests that talk about whether something that are really useful if you're, say, running a tool against a whole data set. I've got 1,000 different programs I'm testing, 1,000 different pieces of software. I'm looking tool A, tool B on each of those. There's a way of saying whether tool A or tool B is better on the whole data set by comparing what it does on each pair. So assigned rank tests, paired sign rank tests will deal with that. There's lots of different tools out there. You've got to know what you're doing. So when students are doing these tests, when faculty are reviewing what the students are doing, make sure they're actually reporting the data right. Also, make sure you have enough tests to have a valid statistical power. And this is where most of us fall down. Say I want to say that tool A is 3% better than tool B. And that's kind of what we're seeing in the graphs I was telling you about. Well, what's the confidence interval? Say I say 3% plus or minus 1% better with 95% confidence. That sounds good to me. 95% likely I am better, plus or minus, 3% plus or minus 1% the other tool. If I look at statistics and the way we do this analysis, this actually requires over 9,000 test cases to reach this level of confidence out of a population of 1 million. So assuming there's 1 million software programs, if I test over 9,000, randomly selected across the whole population, which we often don't do, then I can get this confidence. I'm looking at papers right now that published it on 28 test cases. Well, fine, you won on 28. Statistically, I have no idea if you win or not. I have no idea if you're better or not. Because statistically, the numbers aren't there to convince me. But we're publishing, we're accepting these papers. So, got a few minutes left here, but conclusion, look at the data. Use large random data sets. Don't pick the data set of convenience. I mentioned the Bayo et al. Approach. She used bin utils, core utils, fine utils. These are common Linux utilities. A lot of people use. Why? They're free, they're publicly available, they're small. There's a lot of issues with them that aren't really good distribution of stuff. The spec benchmarks are much better. They're meant to be a better distribution, but there's only 32 of those. We need to find a way to have large data sets that we can test these tools on and see how well they work. And we need to have a way of guaranteeing we know the ground truth. If I'm looking for software vulnerabilities, I need to know vulnerabilities in every piece of code. If I'm looking, the function starts are easier because that I can calculate. I said we should use appropriate statistics, like a paired statistical test. I tell my students consult a statistician. Here at University of Idaho, we have a statistics help center where they can go to say, hey, there's my data. Here's what it looks like. What type of test should I run to compare these? If the data has a small percentage of true conditions, a low prevalence versus false conditions, ignore the true negatives. For faculty, for grad students who are serving on review committees, make sure the committees hold authors accountable on the presenting the results. If they say accuracy, make sure they mean accuracy and make sure accuracy is actually useful. If they're doing other things, just hold them to it. So I said that a little faster than I expected to, but any questions on that? I'll see if I can get here and stop my share. And somebody said something in the chat. I'm not seeing it.
Yeah, so in many cases, random sampling is not possible and the sample sizes are small, but you can still publish results as a case study rather than a formal experiment. This is the case with industry.
Absolutely, but then you got to be clear that's what it is. Which a lot of the papers I'm looking at don't make that clear. Other disciplines do much better. Computer science, cybersecurity, we're not good at this.
Yeah, hi Jim, this is Clem. Can you hear me okay?
Mm-hmm.
Yes.
Yeah. Okay, first of all, thank you for that great talk, and I really appreciate the talk, especially because this is something I deal with constantly, especially in an empirical software engineering discipline where we do this all the time. And you're right, we often do not pay attention to assumptions, to power, to the statistics. And I didn't know the extent to which this was a problem in cybersecurity. And so I appreciate your talk and from that perspective. So thanks.
So, are you hearing me?
Yes.
My question, Jim, is, so how much more work is it to do this extra, analysis that you're talking about 9,000 data sets instead of 28? So how much time does it take?
That's a good question. Depends on what you're doing.
Can you give us
And I have seen people do things on, tens of thousands of test cases and others on a handful. So yeah, the Bayo et al. That I was exampling, they did, 16 variants of 129 programs. I ran the program on my machine. It took 1 week to run and generated 600 gigabytes of data, which most of it was debug data that they didn't need, but they didn't clean it up. Unfortunately, my machine decided to install updates on day 6 out of 7. And I had to restart it.
Okay.
But the main thing, if people can just look at the data, not just, oh, I got this average. I've had students, oh, my accuracy is this, I'm good. But what does that mean? What are you really seeing? Tell me, look at it. And this is not just my students, but the students I see at conferences. I ask them and they're like, what do you mean? What are you talking about?
Hi, Jim. Hi, Jim.
Hello.
Hi, Sola here. I don't know if you can hear me clearly. All right, great.
We can hear you.
Thank you. Thank you so very much, Jim. This really, your talk or your presentation really resonated with me because I'm always excited to see a computer scientist or an engineer talk in a statistical space because that's the space we live in a whole lot. And I really have a huge appreciation for what you are putting together here, that we look at data more robustly and think about the confidence intervals and a number of other issues rather than just the p-value. I do want to say, though, that in our field, more recently, we are actually moving beyond the conventional null hypothesis testing and the overuse of p-values. We are moving into effect size space. And I don't know if computer science is catching up on that, because I know you folks are busy more with the technical details. But statistically, more and more researchers are now advocating for the use of effect sizes rather than the p-values. And also using so many other concomitant statistical, tests or approaches, using the confidence intervals, the effect sizes, the standard errors, and all of those things to make sense of the pattern of findings. So I really like your thinking along that line. I wasn't just sure if effect size is becoming more prominent in your area.
So most of the things, let's see, let's phrase this carefully.
Yeah.
First, a lot of the people have to understand what a p-value is before they can understand it's not good. And they don't even talk about p-values in these reports, let alone saying, oh, wait, no, you really should have an effect size. So we're way behind the curve. I do in my research methods course talk about, I have a slide thing on the dancing p-values and how that just doesn't work, and the effect size and other things, yes.
We're
not there. We're not there yet in a lot of computer science.
It's okay. That's why we all work together. All right. Thank you so much, Jim. Yeah.
Go ahead, Clement. You have another question?
Yeah, I do have another question, Jim. Most of the work that I do in cybersecurity comes from the software engineering side, so I wouldn't call myself a cybersecurity expert. I'm an empirical software engineer that looks at cybersecurity, and so one of the problems we always see in empirical software engineering is the use of the wrong scales, because a lot of the data we collect tends to be ordinal rather than ratio scale. And so, is this something that you've encountered a lot in cyber as well?
Yes. Yeah, they're definitely same type of problem.
Okay.
All right. Are there any other questions from the audience? We've got 5 more minutes.
Noel, this is so lucky. Not really a question for me, but I just want to emphasize the importance of collaborative work here. I think what Jim has presented today is really, really powerful, compelling, and doing this type of work with people in the statistical space, in the social sciences, really can help us take even issues about cybersecurity to the next level. I work with Venera. Venera is a faculty in our, and we're looking at a concept in educational psychology, cognitive load, which is huge. How do software programmers encounter and deal with cognitive load? And with that work has actually attracted a lot of attention and awards. So I see a lot of possibilities and new areas of work as we begin to collaborate and think about bigger, broader issues and how to secure our cyber infrastructure. Thank you so much, Jim. And thanks, Noel. Yeah.
Talking about the cognitive load, it's like, one thing we see is in the software development, software engineering community, there's often a disconnect, disconnect between the mental model of the developers and reality of the system. And to try and get them to make that shift, sometimes it's overwhelming to them. So yeah, that's definitely an area I find interesting.
But it's, Jim, if I may too, I think a lot of times that, sometimes it's unfair to compare the students, because a lot of students come from an engineering background, so they've been taught how to build, as opposed to maybe the natural sciences group of people who've been taught the scientific method. Here's a hypothesis, and this is how you go about using statistics to show evidence for or against something. And so what you're finding is people writing papers using engineering ideas when a lot of times the academics are evaluating the papers from an academic statistical perspective. And so you have a disconnect there that I think we need to all rise to the occasion and try to bridge that gap.
That's fair.
And I think you bring up a very good comment related to some of the domain areas, some of the area, like I'll use cybersecurity related to power systems, right? And so you've got electrical engineers and power that have seen it one way, and then you've got the computer scientists that are seeing it a different way. And how do we bridge that gap? And that's one of our big challenges in multiple different areas is how do we teach both sides how to communicate to each other and work related to that. So I think that's a really great point. And, something that as we talk about having with CySER in general, but we have folks in other areas that are taking the computer science to understand the cyber areas versus the true cybersecurity computer scientists that are also taking classes. There's people are coming at it with different backgrounds, and that can create some unique challenges along the way.
Yeah, I would have to say when I first started working with power people, just getting the vocabulary that when they talked about power security, it was different than when I talked about power security.
Yeah, a little different voltage levels, I think, on those particular cases when we talk there. So
Well, I've always wanted to get at the hacker by sending 10,000 volts back up their keyboard.
there you go. There you go.
At the appropriate amperage.
At the appropriate amperage, exactly. So, well, great. Thank you so much, Jem, for your presentation today. We really appreciate it. Lots of good information, and thanks for the questions, and we'll continue to get the information out. I think we may have had some broken links and some other stuff, but we'll try to get those things worked out. So we look forward to seeing everybody in 2 weeks.
All right, thank you.
Thank you.
Thanks, Jim.
Thank you. Bye-bye.